Welcome to Math TV with Professor V. In this video, we're going to look at how to use the ratio test in order to determine the convergence or divergence of an infinite series. This is a continuation to the first video lecture on the ratio test. So if you haven't watched it already, I'll link it here because that one starts off with more basic examples, and then now this is level 2, spicier, more exciting problems coming your way. Just as a quick recap though, how to use the ratio test. So you have an infinite sum, usually starts n equals 1 up until infinity, and we're summing up the terms an. If the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, if that limit comes out to be less than 1, then we say that the sum of an converges absolutely. If the limit as n approaches infinity, again of that same ratio, ends up being greater than 1, then we say the sum of an diverges. And then the last case, if the limit as n approaches infinity of that ratio equals 1, the ratio test fails, or think of it this way, it's inconclusive. So pick another test, all right? It doesn't give you any information. The series could converge or diverge. It's just the ratio test, sadly, is useless for that particular series. Okay, so let's look at some examples. Use the ratio test to determine if the series converges or diverges. These are the examples we're going to be working on, so strictly ratio test. And first one I want to work on is as follows. It's the sum, n equals 1 to infinity, 10 to the n divided by n plus 1 times 4 to the 2n plus 1. All right, so we know this expression here, that's a sub n. So we're going to take the limit now as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, so a sub n plus 1, to figure out this expression here, I'm going to replace every single n with n plus 1. And be careful, I'm going to have to put some parentheses here on a few of them, so watch carefully. So this is the limit, n approaches infinity. I'll keep the absolute value for now, but we can probably drop them soon. So this is going to be 10 to the n plus 1 over, I need that to straighten up, we're all business today, n plus 1 plus 1, so that's going to be n plus 2, and then this is going to be 4 to the 2 times n plus 1 plus 1. All right, I'm not skipping any steps, but make sure, you guys be so careful, put parentheses, all right, around this n plus 1 so you don't forget to distribute the 2 in just a second. So that's all an plus 1 right here. This is an plus 1. And then we divide that by an, the original, which is 10 to the n over n plus 1 times 4 to the 2n plus 1. And maybe by now you've done a few of them, so you're professional and you already start flipping the second expression and multiplying, but we'll take our time on that, okay? Good. Now n is going to infinity, and notice here our index n starts at 1. So n is not going to be negative. I don't need to keep the absolute value bars anymore in this limit. All right, so let's drop them and then clean things up a little bit. All right, so we've got the limit now. As n approaches infinity, I'm going to have 10 to the n plus 1 over n plus 2 times, now watch this, this 2 when it distributes, you're going to have 2n plus 2, and then there's a plus 1. So that's 4 to the 2n plus 3. Did you see that? Okay, good. Times, and then now I'm going to multiply by the reciprocal of the second expression. So we will have n plus 1, 4 to the 2n plus 1 up here in the numerator, and then over 10 to the n. Okay, so I'm taking the limit of all this stuff. All right, now we want to see what we can cancel. And I'm going to write everything out one more time. So I set myself up so I'm ready to cancel things out. So notice 10 to the n plus 1 sitting up here in the numerator, minding its business. I can write that as 10 to the n times 10 to the first. Okay. Then in the denominator, n plus 2 looks great. I'm looking, here's 4 to the 2n plus 3. And I want to cancel that with 4 to the 2n plus 1. So what I can do is write that as 4 to the 2n plus 1 times 4 squared, right? Remember, when we're multiplying two terms, if the bases are the same, we add the exponents. So 2n plus 1 plus 2, that would give me 2n plus 3. And then times, everything here we can leave alone. n plus 1, 4 to the 2n plus 1, 10 to the n. Okay, and then now you're ready to just cancel a bunch of stuff out. So satisfying. So get rid of this 10 to the n. That is gone. What else? 4 to the 2n plus 1. And then, you know, I thought it would be more exciting. That's pretty much all that happens. Okay, that's fine. So we've got the limit as n approaches infinity. I'm going to group 10 and this 4 squared together because those are just constants. And then I'll write that as 10 over 16 for now. Times, we have n plus 1 over n plus 2. If you want, you could take the 10 over 16 all the way out of the limit, or you could leave it there. It doesn't really make a difference, okay? Let's just reduce it. So this is the limit and goes to infinity 5/8 times. And then notice here, both numerator and denominator are going to infinity. Highest power of n in the denominator is to the first, right? N to the first. So I'm just going to multiply top and bottom by 1 over n. And then we're going to have 1 plus 1 over n over 1 plus 2 over n. And then now as n approaches infinity, 1 over n will go to 0, 2 over n will go to 0. So this whole term approaches 1. And then finally, we're left with 5 over 8. Well, what do I care about 5 over 8? Remember, the ratio test always wants you to compare this limit to the number 1. And since this is definitely less than 1, then that tells me that the original series, the sum n equals 1 to infinity of 10 to the n over n plus 1 times 4 to the 2n plus 1, that series is absolutely convergent by the ratio test. It's optional to say the absolutely part, but remember, if a series is absolutely convergent, then that's the strongest kind of convergence. Of course, it's just going to be convergent as well. All right, how did you like that one? Were you able to keep up? I've got another little spicy guy for you, okay? Next example. Again, we're just using the ratio test on all of these. We have the sum, n equals 1 to infinity, and here is what the terms look like. It's 2, 4, 6, up until 2n divided by n factorial. So I want you to pay special attention to the numerator here. You notice how we only have even factors, 2, 4, 6, up until 2n. That is not the same as writing 2n factorial. Oh no, my friends. 2n factorial means 2n times 2n minus 1 times 2n minus 2, 3, 2, 1. When you use factorial notation, there's no way to skip over the odd integers, for example. Factorial means, this notation means you start with this guy and you multiply by every consecutive integer that comes below it all the way down to 1. So that's why this numerator is written out the way it is, okay? It's not like they had so much fun, they just felt like writing a bunch of products and not using factorial notation. No, they wanted to specify we only want the evens, right? Even integers included in this product. So let's be careful, all right, and keep that in mind. All right, ratio test time. So we're gonna look at the limit as n approaches infinity. And I'm gonna look at an plus 1. So you'll have 2, 4, 6, blah, blah, blah. And then let's see, if I plug in n plus 1, this is going to be 2 times n plus 1 like that. Yeah? Good. And then what would come before it? Well, if you distribute that out, that would be 2n plus 2, right? So what's the next even integer below 2n plus 2? Notice how far apart are even integers. They're always spaced out 2 apart. So the even integer that comes before 2n plus 2 would just be 2n, and then everything else that we've listed, okay? And then in the denominator, we've got n plus 1 factorial. So that's an plus 1. Now, I'm not going to write divided by an. I'm just going to jump straight to where we multiply by the reciprocal. You can put absolute value or not. We know that n's not going to be negative. Okay, so it's kind of up to you, and there's nothing else in here. There's no x's or, negative terms that would require us to keep the absolute value the whole time. Okay, I'm multiplying by the reciprocal of an. So we have n factorial over 2 times 4 times 6 up to 2n. Okay, so let's see here. A bunch of stuff will cancel. Yes, it will. All of these factors, 2, 4, 6 up to 2n will cancel with everything in the denominator here. So all that's going to be left over is 2n plus 2 up top. And then we have n factorial and n plus 1 factorial. So remember, always start breaking down the larger factorial until you hit what you see on the other side to cancel. So n plus 1 factorial, that's n plus 1 times n factorial. I'm going to stop there, because now I can already cancel the n factorials. So all that survives down here is n plus 1. Good? Okay, so now let's see, we've got the limit as n goes to infinity. I have 2n plus 2 over n plus 1. And I notice I can factor out a 2 from the numerator. So limit n goes to infinity, 2 times n plus 1 over n plus 1. Ooh, the n plus 1s cancel. And then I'm left with 2. What do I care about 2? Well, we're using the ratio test, so I always compare the result to 1. And what does that tell me? That tells me that the sum n equals 1 to infinity, 2 times 4 times 6. Yes, you have to write it all out. That's how it is. Over n factorial. What does it do? It diverges by the ratio test. All right. How was that? Good? Okay, I've got a few more for you. Hopefully you're getting the hang of it. That's really the best way to go about these. Example number 3. We have the sum n equals 1 to infinity, n to the 100 times 100 to the n over n factorial. Why don't you guys pause the video, see if you can just set up an plus 1 over an, and then just cancel everything out. I'll take the limit with you, okay? But just see if you can set up the ratio and cancel. Okay, did you try it? I hope you did. Okay, here we go. So we've got the limit as n approaches infinity, absolute value. We have n plus 1 to the 100 times 100 to the n plus 1 over n plus 1 factorial. And then I'm just going to jump straight to multiplying by the reciprocal of an. So we'll have n factorial over n to the 100 times 100 to the n. Okay, did you get the same thing so far? Oh, fabulous. Okay, now we're going to start breaking everything down so we can cancel. So we've got limit, n goes to infinity. N plus 1 to the 100, I don't see too much that we can do, so let's just leave it like that, okay? So we've got n plus 1 to the 100 over, I have 100 to the n plus 1, so I'll write that as 100 to the n times 100 to the first. Then this n plus 1 factorial, we'll break that up into n plus 1 times n factorial. That's going to work out great because I see an n factorial on the other side in the numerator. And then we've got n to the 100 and 100 to the n, all hanging out in the denominator. Okay, so let's start canceling away. We've got 100 to the n, that is gone. N factorial, that is gone. And anything else? No. Okay, so let's see how to work with what's left. We've got the limit as n approaches infinity. And notice here we have n plus 1 raised to the 100 and then n raised to the 100. So let's put those nearby each other. N plus 1 to the 100 over n to the 100. And then who else is left? 100 and n plus 1. Okay, so we still have 100 and n plus 1. And one thing I can do, notice n plus 1 and n are both being raised to the same power. So I can group them together in parentheses and then just raise that quotient to the 100. Watch what I mean. So I'm going to leave this alone, the 100 to the n plus 1. And then now I'm going to write this as n plus 1 over n to the 100, all together like that. Good? Okay, well now I'm super happy because I can write this expression here, n plus 1 over n, in a way that will let me take this limit really easily. So we've got limit, n goes to infinity, 100 over n plus 1, and then I'm going to divide each of the terms in the numerator by n. So n divided by n, that's 1, plus now I have 1 over n raised to the 100. Okay, so I just grouped these together. N divided by n, that's 1. And then 1 divided by n right there. Okay, so then now as n approaches infinity, I know 1 over n, that's going to go to 0. So I have 1 raised to the 100th power, so that's just going to go to 1. And then as n approaches infinity here, I have a constant, and this denominator is getting really, really big. So this whole term is going to 0. So all I'm left with now is a term going to 0 being multiplied by a term that's going to 1. And 0 times 1, that's going to give us 0. Remember, for the ratio test, you always compare this limit to the number 1. So 0 is less than 1, which tells me what? It tells me the sum, n equals 1 to infinity, n to the 100 times 100 to the n over n factorial is, I'll put absolutely in parentheses. You may or may not need to include it depending on the directions. Convergent by the ratio test. Okay, so sometimes the trickiest part of these is just figuring out how to take that limit appropriately at the end. Okay, so you're going to have to think back to some of your limit techniques from Calc 1. Woo, it's been a while. All right, I got 2 more cute ones coming for you, okay? I think we've done 3, so here's example 4. The sum, n equals 1 to infinity. Now this is different here. Let's see, we've got 2n factorial over 9 to the n times n factorial. All right, here we go. Limit, n approaches infinity. Be careful. I'm going to put n plus 1 in parentheses here, okay, and not skip any steps so I don't mess this up. And then in the denominator, I'm going to have 9 to the n plus 1 times n plus 1 factorial. So that's an plus 1 times, I'll put the absolute values for now. We'll have 9 to the n factorial over 2n factorial. Okay, nothing's negative. I see no variables in here other than n, so I'm not going to keep writing the absolute value bars. Now we have the limit as n approaches infinity. Now check this out. This is going to be 2n plus 2 factorial, right? So let's expand it until we run into 2n factorial. Ooh, this can be tricky, but don't worry, I'm here. So 2n plus 2 factorial would be 2n plus 2. Then what's the next consecutive integer below that, smaller than that? 2n plus 1. Keep going. What's next? 2n. Okay, so now I'm going to stop, write the factorial so it can cancel. Then in the denominator, now we've got this 9 to the n plus 1. How should we break that up? Good. 9 to the n times 9 to the first. N plus 1 factorial, that's n plus 1 times n factorial. You're probably super comfortable doing that. Times, and then all this stuff we leave alone. 9 to the n factorial over 2n factorial. Now it's cancel party time, my favorite part. So 2n factorial, bam, bam. What else? N factorial, ooh. Anything else? 9 to the n, yes, very good. Anything else? No. Okay. So now we have the limit as n approaches infinity. We have 2n plus 2 times 2n plus 1 over 9 times n plus 1. I notice here this is 2 times n plus 1, right? 2n plus 2. So I can cancel out this n plus 1. And then now we're left with the limit as n approaches infinity. I have 2 times 2n plus 1 over just 9. So n is going to infinity. That means the numerator is approaching infinity, and the denominator is just a constant. So this limit is going to be infinity. What do I care about infinity? Only that it's greater than 1. That's it. So what does this tell me? This tells me that the sum, n equals 1 to infinity, of 2n factorial over 9 to the n times n factorial diverges by the ratio test. Okay. Are you ready for the grand finale? Here we go. Last one. I almost want to say it's my favorite, but I don't like to play favorites. I think it is, though. Okay, here we go. Sum, n equals 1 to infinity. We have 5 times n factorial squared, over 2n factorial. Okay, how to deal with n factorial squared? I would say don't trip out. Just remember, when you square a quantity, it means you multiply it by itself twice. So that's how we're going to work with it, okay? Don't come up with some weird definition for what n factorial squared is, okay? Alrighty, so we've got the limit. N approaches infinity. Let's write out an plus 1. I'm going to have 5 times. I'm already going to jump to writing it out twice, okay? Instead of using the squared notation. So n plus 1 factorial, n plus 1 factorial, since it's squared. And then we have 2 times n plus 1 factorial. So that's an plus 1. Times reciprocal of the original, so 2n factorial over 5 times n factorial times n factorial. Absolute value for now, but after a quick glance, I can tell I'm not going to need it. Nothing's going to be negative. All right, so we've got the limit. N approaches infinity. We have 5 up here. Now, n plus 1 factorial, you're probably super comfortable breaking that down. It's going to be n plus 1 times n factorial. And then another n plus 1 times n factorial. That's going to work out perfectly because we have these two n factorials sitting down here. Everything's going to cancel so lovely. Now remember, 2 times n plus 1 factorial, you got to distribute. So it's really 2n plus 2 factorial. So start expanding with caution. 2n plus 2. What's 1 smaller than that? Just keep subtracting 1. Don't overthink it. 2n plus 1. Keep going. 2n. Okay, stop here. Then put the factorial so it can cancel with this lovely 2n factorial up here. All right, we're done breaking stuff down. So now I'll write out we have 2n factorial, 5, n factorial, n factorial. Okay, cancel party begins. What do you notice we can cancel? N factorial with these two guys. What else? The 2n factorial's gone. Something else. The 5s, yes, they are gone. Okay, so let's see what we've got left. We have now the limit as n approaches infinity. I have n plus 1 times n plus 1 over, this is 2n plus 2 times 2n plus 1. Okay, just like last time, remember we could take the 2 out, and this is 2 times n plus 1. Let's cancel it with one of the n plus 1s left over in the numerator. And then now we have the limit as n approaches infinity, just n plus 1 up here, over, I still have this 2 and 2n plus 1. So if I distribute, now it's 4n plus 2. And as n approaches infinity, both the numerator and denominator are going to infinity. When you have a rational expression like this to take the limit, we're just going to divide by the highest power of n in the denominator. I try to avoid using L'Hopital's rule because then you're going to have to define a function, right? Because sequences, terms with n are not differentiable, so you can't use L'Hopital's rule the way it is right now. So I try to avoid it, okay? So we're going to divide by n. And then now we're going to have the limit as n approaches infinity. 1 plus 1 over n, and then in the denominator this is 4 plus 2 over n. And then now we can see, okay, 1 over n, that's going to go to 0 as n gets big. 2 over n goes to 0, and we're just left with 1/4. Well, what do we know about 1/4? It's less than 1. So now we can make our conclusion. This means that the sum, n equals 1 to infinity, 5 times n factorial squared over 2n factorial converges. You could say absolutely if they ask by the ratio test. Okay. Yes, you should always rewrite the original sum at the end when you're saying whether or not the series converges or diverges, and state which test you used. This is a complete answer. All right, hope you found the video helpful. I figured I'll do more spicy examples for all the video lectures that I've already made, just in case you guys need more exposure and see more scenarios. So coming up next is going to be the root test, and then I'll talk more about absolute, conditional, convergence. Just more examples, the more the merrier. Don't forget to give this video a thumbs up if you found it helpful. Please subscribe if you haven't already and share it with your classmates, your friends, your neighbors, your gardener, your nail tech, whoever would benefit from learning about the ratio test.